Development Program. This session is about analytical methods and other methods of characterization in materials research. First, I would like to request Convener FDP, Professor and Head, Department of Chemistry, Dr. Kavita Sharma, for virtual floral welcome of our guest, Dr. Sankara Narayana.
Once again, welcome you, sir, in this FDP as resource person. Thank you very much for accepting our invitation.
Before starting the session, I am going to introduce the eminent speaker, Dr. Sankara Narayan. Dr. Sankara Narayan is Professor Emeritus at Department of Analytical Chemistry, University of Madras, Chennai, India. His area of specialization and interest includes additive manufacturing of metals, biomedical materials, surface engineering, corrosion, tribocorrosion, and nanomaterials. He obtained his doctoral degree in chemistry from University of Madras in 1992. He was a postdoctoral fellow at Baylor University, Texas, USA during 1994-1997. Senior Research Associate at Indian Institute of Technology, Madras during 1997-1998. Scientist in CSIR National Metallurgical Laboratory, Chennai from 1998 to 2012. Visiting scientist under Brain Pool Program at Yonsei University, Seoul, Republic of Korea during 2005-2006. Research professor at the Department of Dental Biomaterials, School of Dentistry, Chonbuk National University, JNU, Republic of Korea during 2012-2017. And research professor at Ulsan National Institute of Science and Technology, Ulsan, Republic of Korea during 2018-2019. He has published more than 200 research papers and 15 book chapters. He is the principal editor of 2-volume series on surface modification of magnesium for biomedical applications, published by Elsewhere Sciences. He is the co-editor of the book on conversion coatings for magnesium and its alloys, published by Springer. He has 2 patents to his credit. He is a mentor, motivating young researchers to achieve their goals in is what he considered as his greatest asset. His papers have been cited more than 8,794 times with H index of 50 and I-10 index of 108. Besides his research and development work, he is also a freelance science writer and an educational consultant. We are very thankful that a great educator and researcher, Dr. Sankara Narayan, is with us. I am requesting you, sir, to start the session. Sir, please.
Thank you, madam, for the nice introduction, and thank you, Dr. Kavita Sharma. And I'll be going through the presentation. Can you able to see the slides?
Yes, sir. Slide is visible.
Okay, fine. So today I'm going to talk, since it's a workshop or a faculty development program on analytical chemistry. So I'm planning to give a short lecture on analytical methods and other associated methods for materials research. That will be my first talk. And then my second talk will be on my research program on magnesium as a biodegradable implant. So first, let me give a brief talk about analytical methods and other methods of in materials research, because basically I'm a chemist, but I have done a lot of work on material science, particularly on biomaterials and other aspects, corrosion and coatings aspects. So how these analytical techniques are useful in understanding the chemistry, the mechanism, all those things. So that's what I'm going to study. We have been working on the magnesium-based biomaterials. What is magnesium-based biomaterials? Actually, you know that as a chemist, you know that magnesium is a highly reactive material, okay, and it undergoes corrosion at a much faster rate. Normally, when we want to develop an implant material that is going to be put it in the human body, we generally believe that it should be very much highly corrosion resistant, because the body fluid is highly corrosive. It contains a lot of chloride ions. So we should put a material only with this highly resistant. So that is why initially they started with the platinum, gold, and then they come to titanium-based materials and 316 low carbon vacuum remelted material. So these are the materials used for developing an implant. Then later the strategies changed. The strategies changed that the implant material need not be in the human body. So the purpose of implant, if there is a bone get fractured, automatically we are putting an implant. So the purpose of the implant is to help to hold the bone, fractured bone, and until it gets healed. So once the bone gets healed, the fracture gets healed, the metal implant is no longer necessary. But if we want to remove that, we may have to go for another revision surgery to remove that implant. It is a painful thing, and it's a costly affair, and all those things are there. So scientists have thought that, many researchers have thought that, why don't we develop a degradable implant? Polymeric materials and metals have been considered. Among the polymeric materials, polycaprolactone is the best material and recommended materials approved by US FDA. But the polymeric materials, they don't have enough strength. They don't have enough strength, so they cannot be used for load-bearing applications and all. So then they considered metals. Among the metals, magnesium is considered as a very good choice. We know that, I already mentioned, magnesium is a highly active material. It is undergoes rapid corrosion. So how can we use it? But the requirement is that if you could be able to push the material and improve the corrosion resistance by some extent, then definitely that can be used as a degradable implant material. So that's why the magnesium research has started, and we also did that work for more than 10 years by now. In the process, we have developed some method. Actually, when we are doing a corrosion, we have to monitor the corrosion behavior of magnesium to understand how fast it is corroding in the body fluid. So we use a simulated body fluid and do the corrosion testing and see that how fast it is corroding, basically. One of the methods is there are electrochemical methods out there, like potentiostatic polarization studies are there, electrochemical impedance microscopy studies are there. So these are the classical electrochemical measurements to understand the corrosion behavior. But many people feel that long-term immersion is the most realistic solutions. Long-term immersion is the most realistic way that we can able to do that. So immersion test in simulated body fluid, particularly over a longer period of time, is considered to be more realistic than the accelerated electrochemical. In this immersion test, what you do is, when you're immersing the magnesium sample in a simulated body fluid, what happens is magnesium undergoes corrosion. And so one of the reaction is that is the anodic reaction. Dissolution of magnesium from Mg2 plus 2 electron is the anodic reaction. There will be corresponding cathodic reaction, that is reduction of water and then evolution of hydrogen. So that is the cathodic reaction. So during that, because of the consumption of the H positive ions, there will be a rise in pH. Okay, so we will be monitoring the extent of change in pH of the simulated body fluid as a function of time. So that is the normal method that we are practicing it. And if the extent of change in pH is much higher, then you can able to understand that the magnesium is corroding at a much faster rate, like that. You can also calculate the mass loss as a function of time. That also can be used. But generally, mass loss is recommended only for materials which undergoes uniform corrosion. But magnesium undergoes localized corrosion, like a pitting type of corrosion. So generally, mass loss is not that much recommended. So many people are following the extent of change in pH or the extent of hydrogen evolved from the material during the reaction. That is followed. And it is generally understood that it is the higher the rate of change of pH, higher the rate of corrosion. So that is what we mentioned about it. What is the challenge in this measurement? pH, of course, you can use a simple pH meter, you can measure that. But important thing is the pH, that the electrode, the glass electrode that we are using it for the pH, for measuring the pH should be properly calibrated. Okay. And in cases, suppose people are developing new alloys, magnesium alloys, with a closer variation in chemical composition. When people are developing alloys, magnesium metal alloys, what they will do, they will add alloying elements to various proportions. It's about 1%, 2%, 5%, 10%. Like that. So when we are adding alloying elements of different fractions and they develop a magnesium alloy, when we use the pH measurement, the rate, extent of change in pH is not much. So we have a difficulty in rating the alloys, newly developed alloys, whether which one is giving a better corrosion resistance. That is very difficult to tell only from the change in pH measurements. This is applicable also for suppose if you are doing a small surface modification by applying a coating on the magnesium. Okay, there will be small, and you are varying the operating conditions of the coating process. Then, if you are subjecting to corrosion testing, then it is very difficult to monitor the change in pH. So we thought this is a problem, and then we would like to develop a simple method. Okay, one of the methods that we have developed is a spectrophotometric method. So we want to develop a spectrophotometric method. So normally we use a Hanks balanced salt solution, which is a simulated body fluid. And what we did is we have added phenol red as an indicator. So why? Because we want to follow the method, the corrosion process by a spectrophotometric method. It's basically, it is an analytical. We want to develop an analytical method for monitoring the corrosion behavior. So we have prepared a simulated body fluid that's called Hanks balanced salt solution. And we added a small quantity of phenol red as an indicator. Phenol red is a red in color. It pH sound because the simulated body fluid is 7.40 because body fluid the pH is 7.40. So we modified it to 7.40 and we maintained the temperature of the solution as 37 degrees centigrade. It's body temperature. And what we did is we measured the change in absorption of the solution because it's a colored solution. We are adding the indicator solution, so it becomes colored.
Excuse
so
me, sir. Sir, sorry to interrupt, but slides are not moving.
Oh.
We are still on first slide.
Now it is moving?
Yes, sir. Yes, sir.
Okay,
yes,
and then I have to move to make it in this presentation. So let me repeat it. So we have developed a spectrophotometric method to monitor the corrosion behavior of magnesium. And basically, we generally electrochemical measurements normally people follow, but it is generally believed that immersion test performed over a longer period of time is more realistic than the accelerated electrochemical test. So one of the things is what we want to do is we want to measure the change in pH of the simulated body fluid. Okay, but the problem is we can measure the pH change in pH of the medium using a pH probe or pH electrode. But if you are developing magnesium alloy with a closer variation in the chemical composition, or if you are slightly modifying the magnesium with a coating prepared under varying conditions, okay, varying process parameters, then there will be much change in the pH among the things. So it is very difficult to rank the magnesium alloys, newly developed magnesium alloys, or the type of coating. No, so different variations. Say, for example, if you are preparing a coating at 2 different temperatures or 3 different temperatures, and then measure the change in pH, there won't be much change in the pH among them. So which coating is better? So you cannot rank it. So to avoid that, so we want to develop a spectrophotometric method. The idea is to develop a simple method. Okay. So we used the Hanks solution as the simulated body fluid. What we did is we have added phenol red as an indicator in the solution because we want to follow that in the corrosion of magnesium process by spectrophotometric method. So what we did is we modified the solution and taken the samples as a function of time and measured the change in absorbance of the solution. Because it's a colored solution, we can monitor the color absorbance of the solution. And in the process, our main aim is to analyze the data and establish a correlation, whether there is a correlation between the change in pH and change in absorbance of the phenol modified solution as a function of time. If there is a good correlation between the change in pH and change in absorbance, then we can we can monitor the rate of corrosion or the corrosion behavior of magnesium by spectrophotometry. So that is our idea during this method. So what we did, we initially measured the pH of the simulated body fluid solution, which is modified with the phenol red solution as a function of time. So initially, this is the color of the solution, and as a function of time, we monitored the change in pH. So this is the change in pH. It is initially there will be a rapid change in pH. Subsequently, it is followed by it tend to saturate it. Because initially the magnesium is freely available, all sites are available and is freely corroding. And with the time when it reaches around 800 minutes and all, so there will be a formation of a corrosion product. The surface is covered with the magnesium hydroxide. As I said, that there will be increase in pH at the interface in the metal solution interface. So there will be magnesium hydroxide formation. So once the metal surface is covered by magnesium hydroxide, the rate of increase in pH is getting saturated. But it reaches around 8.4 during a 1400 minutes. So this is the type of color change from the initial to the final, about 1400 minutes. 1400 minutes, we follow the process. So we measured the pH of the solution, and we also measured the we also recorded the absorption, UV visible absorption spectra of the modified solution. Because the phenol red is the colored solution, so we measure the UV visible absorption spectra as a function of time. So we could be able to see that there are two different peaks, one at 433 nanometer, the other is 550 nanometer. As a function of time, if you see that there is a decrease in the intensity of the peak at 430 nanometer, and there is an increase in the intensity of the 550 nanometer. This is due to the change in the structure of the phenol red as a function of due to protonation and deprotonation reactions. So there will be if there is a continuous increase in the absorbance at the 559 nanometer as a function of time. So what we thought that if we measure the absorbance of the solution at 559 nanometer, that we want to do it. So we measure the absorbance of the solution, H solution at 559 nanometer as a function of time, and you plot it. Okay, and this also follows a sigmoidal fit. Okay, the data also follows a sigmoidal fit. Then what we did, we established a correlation because both axes are time axis. pH versus time is a time axis. Absorbance versus time is also a time axis. So the time axis is the common axis. So we established a correlation between the absorbance of the HPS measured at 559 nanometer as well as the pH of the HPS. So we plotted, and we could be able to see a very good correlation between these two parameters. So based on this correlation, so what we inferred is it is possible for us to measure the absorbance of the solution and correlate with the pH of the HPS. So we already said if there is a rapid change in pH of the Hang solution, then there is a rapid increase in corrosion. So if we follow the absorbance measurement, if there is a very good increase, if the absorbance is very high, then automatically we can say that the rate of corrosion is very high. So based on that, why we have to use absorbance measurement? People may ask why we have to use absorbance in the spectrophotometric method when the monitoring the pH is a much easier method. Definitely, I agree that pH measurement is the simplest and easiest way to monitor the change. But absorbance measurements are more accurate and reliable. Because pH variation, sometimes if you don't properly calibrate the pH meter, or if you don't keep it the glass electrode in acidic medium during the storage time, it might not properly sense. Okay, so that problems may be there. Okay, these are, and pH measurement compared to pH measurement, absorbance measurements are more sensitive. Even there is a slight change in the color of the solution, you can able to measure the absorbance of the solution. So that is the advantage of measuring the absorbance of the solution and measuring the pH of the solution. So this we have established, and we have developed a simple analytical method to monitor the corrosion rate of magnesium. So this is the paper is published in a good journal on corrosion science, and a few years back we did that. And but the limitation. So every study has certain limitations. So the limitation of the study is that this indicator, phenol rate that we have used as indicator, has a limit. So beyond 8.4, there won't be any change in color. There won't be any change. It reaches almost a pink color and then it remains stable. There won't be much change in the absorbance value beyond 11, beyond 8.4 pH. So suppose if you change the medium from, suppose if somebody want to monitor the corrosion behavior of magnesium in a sodium chloride medium. In a sodium chloride is highly corrosive. So if you put magnesium in sodium chloride medium, the pH might rise up to 9.5 to 10 sometimes. So we cannot use phenol rate as an indicator for that because the limitation is only 8.4. So we cannot measure the absorbance beyond that point. So we have developed another method similar to this using universal indicator. Instead of phenol rate, we have used universal indicator, and that is also published in a journal. So the idea that I want to emphasize that it is possible to use simple analytical methods. So the significance of analytical chemists lies in the method development. Analytical chemists are the best people to develop methods to help materials researchers as well as other researchers in developing developing a method as well as to understand the mechanism of these things. That's what the analytical tools are all about. Okay, a few years back, I was working in National Metallurgical Laboratory, Chennai. There, one of the company from Chennai, they came to us. They are the manufacturer of tiles, and they have used blast furnace slag, which is a waste material produced in steel making industry. Okay, so there is several tons of blast furnace slag are generated, and the government is encouraging people to use the waste material. Okay, the slags generated from the steel industry. So for that, the government has given is ready to give some subsidy for the companies who are willing to use a large quantity of the blast furnace slag. Materially, generally, construction industry can use a lot amount of this materials, fly ash and blast furnace slag. So they used this blast furnace slag and developed the tiles. So when they approached the government to claim the subsidy, so they are telling that we have used blast furnace slag. The condition is they have to use at least 25% of the blast furnace slag in the finished tile. So there was a question raised by one of the officers. What is the guarantee, or how I could be able to see that whether you have used 25% of the blast furnace slag or not? How do I know? Because you are giving me a tile and you are showing that you are using the blast furnace slag. They cannot come and do the policing work every day. Officers cannot come and do the factory and then do the policing work. So what is the guarantee? Is there any method to show that you have used 25% of the slag in developing the tile? So that was a big challenge. So when they came to us to National Metallurgical Laboratory, and I was in the chemistry department, so it was a really challenging problem. And we discussed with the company people, and we are asked what all the material they use. They said they are using sand, they are using cement, they are using M-sand type of thing, jelly. So, and in all these things, all materials are there. Silica, alumina, iron oxide, all those things are there. Okay. And in blast furnace slag also, the composition is similar. So when you are using multiple materials and all these materials, alumina, silica is there in everything. So how to identify whether how much blast furnace slag is there in the finished type? So what we did is we have gone through the composition of all the materials, and finally we found out a tag. Okay, we found out a tag that the manganese oxide is very specific to blast furnace slag because it's a steel. In the powdered type, we made a fusion. We made a fusion, and then we analyzed the manganese content by atomic absorption spectrophotometry, and we correlated the blast furnace slag, and we found out that how much percentage they are using for every batch or every type of thing. So it becomes a continuous business for us for the laboratory. So the idea is that we have developed a very simple method, basically using manganese oxide as a tag. So why I'm telling this now, the analytical chemists, they have a lot of role to play in method development. Many of the things are very challenging problems. So that's what I'm telling. There's one more challenge, that we were given a sample by the customs department. So we might know that people are importing scraps and then waste materials, and they are using. So one of the importer, they brought out some aluminum metal powder. Okay, and they claimed that it is a scrap material because you know that the duty is different from the scrap material as well as the metal powder. So metal powder means high duty, and the scrap means it's low duty. So what is their claim is no, it is a scrap because all the aluminum powder is already converted to alumina. L2O3 or converted. There is there's no way that we can use it as aluminum powder. So the customs department has taken the sample and they have sent to us, and then they are asked us to determine how much aluminum and how much aluminum oxide are there in the aluminum in the powder. So it was a challenging problem because normally aluminum will undergo aerial oxidation and it will be covered with a thin layer of alumina. So basically, if you analyze it on the top of the surface, it will be alumina, but in the core, that will be aluminum metal powder only. So the government wants to fix a duty based upon how much aluminum content is there. That's what the customs department has decided. So it is our job to develop a simple method and identify how much aluminum and how much aluminum oxide are there in the metal powder. So that was a challenge given to us. So what we did is, myself and my colleague, we developed a very simple method. Okay, metal powder generally, they react spontaneously with acid. You put hydrochloric acid, particularly, aluminum will immediately react and generate a lot of hydrogen evolution will become as a side reaction, because metal dissolution is the anodic reaction and hydrogen evolution will be the cathode reaction. So a lot of hydrogen evolution is coming. So we thought, we want to use a simple gas evolution apparatus. Simple, you might have seen, gas evolution apparatus. So on the volume of the amount of hydrogen that is evolved from the metal could displace the volume of the liquid. So based on that, we can able to develop a method to determine how much aluminum metal powder is there. So we bought standard aluminum metal powder, and we varied the concentration of the quantity of aluminum powder, and we developed we measured the volume of hydrogen displaced for every quantity, and we established a calibration curve, and then we tested the unknown sample, which is covered by a alumina layer. So in that way, after some time, we could be able to see that metal will completely dissolve and aluminum oxide will not react that much. So based on that, we estimated that sample, how much aluminum could be there and how much is covered by alumina layer. So based on that, the customs department has put duty. So this is another interesting, very small work only. It's not a very big work like analytical chemistry work. Okay, so very simple work. So the idea that I'm emphasizing is that analytical chemists have a significant role in developing methods and problem solving. Very simple applying the analytical chemistry methods. A few years back, one of my colleagues, my former colleague, Dr. Tyagarajan, now he's a scientist in National Aerospace Laboratory. So he has developed a simple method. Okay, so normally we use the reagent dithesone for the determination of lead, cadmium, and mercury by spectrophotometry method. By complexing, it's a complexing agent. It forms a colored complex, and then we measure the absorbance by spectrophotometry method. His basic work is development of a chelating resin for removal of heavy metals. Okay, and he has used the spectrophotometric method for determining how much metal ions are retained in the resin, and then how much is coming out. So all those things he did, and he has used dithesone for the determination of lead. Okay, normally the dithesone reagent is prepared in a chloroform solvent, but the stability of the dithesone dissolved in chloroform is very, very less. So normally we prepare a stock solution of 0.01% dithesone, and for dilution we make it as 0.01%. But what happens is, even the freshly prepared chloroform solution, prepared solution in chloroform deteriorated very quickly. The main purpose of deterioration, main cause of deterioration is that the photochemical degradation of chloroform that leads to that generates phosgene, and that abstracts the hydrogen from the dithesone. So this is the reason for the degradation, the rapid degradation of dithesone. Dithesone is a bit costly. So, and the stability is poor. Not only the cost, the stability of the solution is poor. So we have to prepare every time fresh solution, and that is a problem. We cannot store it for a longer period of time. So we developed a method, okay, by various addition agents. And one of the agents that he has tried and successfully developed this is the addition of acetic acid. Because acetic acid could hinder the degradation of the dithesone by forming a hydrogen bonding, and that prevents subtraction of hydrogen. So he has prepared a dithesone chloroform solution mixer, which is modified with a 6 molar acetic acid. Okay, that is found to be more stable even when it is exposed to the sunlight, or even if it is high temperature. So it is both thermally stable as well as photochemically stable, this reaction mixer. So it is possible for him to prepare a stock solution using a 6 molar stock solution, and it's stable for at least 1 month. Normally this solution is stable less than few hours. So he has developed a method by the simple addition of acetic acid and improve the stability of the reagent used for spectrophotometric determination from 1 week to 1 month. Sorry, not 1 day to 1 month. So that is the advantage of this methodology. So again, I'm telling them, analytical chemists still have a major role to play. It may be a simple methodology. You need not have, as an analytical chemist, you need not always have hyphenated techniques and other things. Then only you can able to do analytical chemistry. It's not like that. So I want to emphasize, there are simple solutions are always there. There are a lot of problems in analytical method development. You take simple solutions and then develop methods. So that is good for many people. Okay. Now I'm going to come into my research area, some of the research area that I have done, and how many surface analytical techniques are useful in understanding the mechanism of this materials research. One of the work that we did is fretting corrosion. Fretting corrosion is involves corrosion means it is the interaction between the metal and the environment that leads to the degradation of the material. So that is the definition called corrosion. Fretting is a small amplitude movement, it's in about micrometer level, small vibrations, okay, fretting. And we have studied the fretting corrosion of tin-plated copper alloy electrical contacts. So where it is used, these tin-plated copper alloy electrical contacts are used in automotive materials. See, nowadays you might have seen automatic car chases, everything it is dashboard, everything is automatic electric control. Okay, so behind that, all these electrical contacts, then there are copper alloy coated with the tin. So why they are coating with the tin means normally we can coat it with gold and things, but they are very costly. The simplest solution is plating the copper alloy with the tin, because tin is electrically conducting. That is more important. Tin is electrically conducting and it's cheaper. So they normally coat the copper. Copper alone cannot be used because copper gets easily tarnished by reacting with oxygen, that will increase the resistance. So they coat with the tin because tin is could be able to offer a good corrosion resistance for copper. And then tin is highly conducting also. So they coat the copper alloy with the tin. So normally the electrical connector contacts are like that, particularly used in automotive industries. But the problem is during running or during in idle condition in a signal, so there will be a lot of vibration in the vibration in the vehicle. So what will happen? This electrical connector contacts comes in contact with each other. So there will be movement, small amplitude movement, and that leads to removal of the tin-plated material. So I will explain it. So we have developed a simple setup to study the fretting corrosion behavior in the laboratory. This work I have done it in Korea. Okay, so this is the sample, copper alloy brass sample coated with the tin, and this is a flat sample, and this is the rider. Maybe we made a small punch to create a ball-on flat contact configuration. So this is the arrangement that they may use. It's a flat sample, and then it's the rider sample. And during the small amplitude vibration, there will be movement, and the tip of that rider could be able to remove the tin plating, small amplitude vibration. And we measured we connected to the circuit, and we measured the resistance of the during this. So this is the way we have done it up to 48,000 cycles. Okay, what happens is during the initial period, the resistance is very, very low. Okay, resistance is very, very low. So the resistance is around only 0.1 ohms. Up to 8,000, nearly about 12,000 cycles, there won't be any problem. There is no any problem. Beyond that, the contact resistance starts to increase. And when we go to the third stage, beyond say 18,000 or 17,000 cycles, what happens is the resistance is increased more than 10 and reaches even 100. So that means it automatically becomes an open circuit. So your dashboard will not work, your particular indicator will not work. Okay, so we should not reach this stage. We should be able to prevent at this stage. So we need a proper understanding why the tin-plated copper alloy contact is getting corroded or getting fretted, and the material is removed, and how it is getting corroded. So that's what we need to understand. Okay, so if you take use scanning electron microscope. So how scanning electron microscope is useful to understand the mechanism of fretting corrosion of tin-plated compound. So this area is very small. You can see that the entire area. So this is a 200 micrometer scale. Okay, so this is about 400 to 500 micrometer only. Normally we started with the 180 microns. So this is the movement. This is the movement, and it generates slowly. It comes in an elliptical. So this is a scanning electron microscope photograph, and we have taken the high resolution images at the central region as well as at the peripheral region. So you could be able to see that at the peripheral region, there is a lot of white powders and the very big size powders. In the central region, there is a mixture of materials, particularly with copper and tin. So this is one information that we got from the scanning electron microscope. And we did EDX line scanning across the fretted zone. So across the dotted line, we did the EDX line scanning. So what the EDX line scanning is telling about that? So you could be able to see this is the line for tin and this is the line for copper. So this is the fretted region. What happens is in the fretted region, the tin plating, the tin has come down from here to here. Okay, this is the other regions of tin is very high. Okay, in the fretted region, the copper is very high. So that what does it means? The tin plating is completely more or less is removed, and the underlying copper is exposed. So that means the coating is already removed, and you could be able to find some oxygen. So what has happened during the atmospheric exposure to the atmosphere? You could be able to see. You can correlate that will be a formation of tin oxide. That will be a formation of copper oxide. The zinc from the alloy. It's a copper zinc alloy basically. So the tin and oxygen indicates the formation of tin oxide, and copper oxide also is possible. So this is the pattern that we are getting from the EDS line. So EDS line scanning can be effectively used to analyze the changes in the material behavior, and then you can be able to correlate the result. We also did X-ray elemental mapping. Elemental mapping is very good to understand the mechanism. See, for example, this is the scanning electron micrograph. This is the fretted area. This is the damaged area. Okay, and we analyze for tin, copper, and oxygen. You can see there is a hole. There is no tin. So that confirms the EDX line scanning also. Sorry. I'm sorry. So it can confirm there is no, you can able to see that the tin is completely removed. This is subsequently supported by the elemental mapping result. There is no tin here. And there is copper. So the copper is fully exposed in this area, and there is oxygen in this area. So we could have formed copper oxide as well as tin oxide. Particularly the tin oxides are in the surrounding area, and the copper oxide in the middle area. Copper and tin oxides are in the middle area. So we could be able to understand the fretting corrosion behavior and how it is getting oxidized. We also take an EDX pattern, okay, at different regions. So this is the bright white particles present at the edge region. At the edge of the region, you could see that there is a lot of tin and copper and oxide also there. Okay, so that way, this is another EDS line scanning pattern as a function of various as a cycle. Actually, no, let me put it actually. These two figures. I would like to put again. Okay, so this is we have taken the entire fretted region. You could see that a lot of tin is there because we have taken the entire sample area, and only the damage area is limited only 200 microns or 500 microns. So there is plenty of tin in the entire fretted region, and the copper and zinc from the base metal, and there is small amount of oxygen is there. Okay. I'm sorry. What I have to do is to go down and then, yeah. So this is the white particles present at the edge regions. So white particle present at the edge regions mostly are tin content. Like that. Yeah. This is the EDS line scanning pattern performed across the fretted zone as a function of fretting cycles. So what happened is after 30 cycles, okay, you could be able to see the tin is there. Copper is there, and there is no amount of oxygen, very low amount of oxygen. So it is very clear that after 30 cycles, the damage has not occurred. Okay, after 30 cycles, the damage has not occurred. So that is the we could be able to see. And after 1,000 cycles and 8,000 cycles, what happens is after 8,000 cycles, the tin is completely removed in this area, and copper is coming up very nice. So you can able to using the EDS line scanning pattern, EDAX pattern, as well as the X-ray elemental mapping and scanning electron microscope, all put together. You use a scanning electron micrograph, and you use the EDS line scanning pattern, use the X-ray mapping, as all those things, EDX pattern, everything you've been able to see and understand the mechanism of corrosion, how it is the metal is removed and it is getting oxidized. So normally we can say that tin is highly conductive. Why the resistance is increasing? Because tin is highly metal and is highly conductive. But the moment tin is removed and it is exposed to the oxygen, tin and copper are exposed to the oxygen, it may get oxide, tin oxide and copper oxide. These oxide materials are poorly conducting. So that is why your contact resistance is increasing. So what happens is, if you put this electrical contact in automotive thing in the hood, okay, what happens is there will be rise in temperature also. So that aggravates, that accelerates the rate of oxidation. Okay, like easily tin oxide could easily form at high temperatures. Okay, so this is the main problem. So if you allow that there is a small vibration in the motor vehicle, that will lead to small amount of fretting, and that removes a tin metal, and then leads to the formation of tin oxide, which is poorly conducting, and automatically your electrical conductor becomes very poor. Your electrical conductor failure, and a conductor will fail, and your dashboard will not show the indicators problem. So this is the problem with the fretting corrosion. So I've explained some of the analytical methods, how it can be, these methods can be used to understand the mechanism in the problem. You might have heard about, you might have studied glancing angle X-ray diffraction. So what is the difference between a powder X-ray diffraction and glancing X-ray diffraction? Is the angle of incidence of the X-ray beam. Normally, if in a powder X-ray pattern, the angle of incidence is maybe more than 45 degrees. So it will penetrate through the depth and then it will come out. So you will be able to get a X-ray diffraction pattern for many samples. It's not a problem. But if your material is a thin film, it's a very thin film deposited on a substrate, then if you do a normal X-ray diffraction pattern, what will happen? The X-rays will penetrate through the thin film to a longer distance. So automatically your base metal peak will come in a very high way. And the thin film, the characteristic peaks of thin film becomes very, very low intense. Normally, we may confuse whether it is a noise or the peak to the characteristic peak to the particular material. So in that cases, we can use very well the glancing angle X-ray diffraction. Okay, so this is one of the example. I have deposited a fluoride coating, fluoride conversion coating on magnesium. But how we prepare? We take a magnesium sample, we put it in a 48% HF. There is a concentrated HF, 48% HF at room temperature for 24 hours. So this is the way that we develop a fluoride conversion coating. So normally I said magnesium is highly reactive. Okay, and if you are putting it in acid, it will undergo rapid corrosion. But the only one exception is if you put a magnesium in a concentrated hydrofluoric acid, 48% hydrofluoric acid, commercial grade. Okay, there will be a hydrogen evolution only for a few seconds. Then immediately a passive film will form on the surface. Yellow color passive film will form on the surface, and that is due to the formation of magnesium fluoride. Magnesium dissolves and reacts with the HF and forms magnesium fluoride. So that is called fluoride conversion coating. So it's a very thin film. The thickness of the film is less than 1 micron in most of the cases. Even if you increase the time, it is not possible to increase because it is a conversion coating. The basic of conversion coating is something the metal should dissolve, react with the environment, and then again deposit as a coating. That is the mechanism of conversion coating. So once the surface is covered by a magnesium fluoride layer, there won't be any further dissolution of metal, magnesium metal in the acid. So there won't be any chances of developing a thickness of the film. So the fluoride conversion coating is very thin, less than 1 micron most of the times. And we cannot use a normal powder X-ray diffraction pattern to determine the what are the composition, what are the various phases present in the material. So in these cases, glancing angle XRD is very useful. So this is the glancing angle XRD diffraction pattern of fluoride conversion coated magnesium sample. So you could be able to index it very clearly. So these are the red spots are magnesium peaks. You could be able to see how much intensity magnesium peaks are. So that clearly shows that the thickness of the film is very, very thin. Okay, even in glancing angle XRD, it is coming like that. So glancing angle, no, the angle of incidence is about less than 5 degrees or 10 degrees. So that way you have to go take it. So we could be able to identify the formation of magnesium fluoride using glancing angle XRD. This is one example. And with respect to scanning electron microscopy, you have used the scanning electron microscopy. So how you could be able to use an analytical technique like scanning electron microscopy to understand the evolution of morphological features. This is particularly for a coating. Okay, that's what I'm going to explain this. Okay, say this is a morphological feature. We have deposited a brush-shaped coating. This basically is a calcium phosphate, CaHPO4 2H2O. So we can able to see during the initial period the crystals are formed here and there. Okay, the crystals are formed here and there. It is not, I put the animation and it's not. Okay. And after 5 minutes, you could be able to see the size of the crystals are growing. And after 10 minutes, you'll be able to see the surface, entire surface is covered by the brush-head crystals. So you could be able to see the evolution of the morphology of the as a function of time. So for that, scanning electron microscopy, technically scanning electron microscopy can be effectively used. So another example is that, okay, the same thing, same coating as a function of time. So how the brush-head crystals are attached to the base coating. There is a base coating of plasma electrolytic oxidation coating that I have done, and over that I'm depositing the brush-head crystals. So how exactly the brush-head crystals are attached to the earlier coating? What is the placement? How it is fixed like that? So that is what, as a function of time that I have monitored. So after 7 minutes, you could be able to see it is attached and then it is growing like this. So you could be able to see the evolution of the growth pattern of the crystals very well by monitoring by scanning electron microscopy as a function of treatment time. So take the samples at different time intervals and then measure the scanning electron microscopy. Take the scanning electron microscopy pictures to be able to understand the mechanism, how the crystals are developing over the material. Okay. Another method that we have done is the surface mechanical alteration treatment. It is a plastic deformation of metals. Okay, and how we can use the scanning electron microscopy to understand the microstructure changes. It induces plastic deformation. There will be a change in the microstructure. I will explain it. So this is the schematic of the surface mechanical alteration treatment. What happens is we have two chambers, and inside the samples are placed on the top of the pot. Okay, and we put balls. Okay, steel balls. This is stainless steel sample, fixed, and we put a steel balls in the panel, and then it is this will be vibrating like this at a particular frequency, 50 hertz. So it will be vibrating like that. So there will be rapid, random movement of the balls. The balls will jump up and down, and that will directly impinge on the surface of the metal, the top surface of the metal, and that induces plastic deformation. So this process induces a plastic deformation, and there will be a change in the microstructure of the material. So how scanning electron microscopy can be effectively used to understand the change in microstructure? What type of changes have occurred? So this is for the changes in mechanical, change in microstructures of a stainless steel sample, 304 grade stainless steel sample. We are treated by this surface mechanical alteration treatment using 5 mm dia ball and 8 mm dia ball for various treatment time. So if we use 5 mm dia balls, we could be able to see there is some formation of mechanical twins and the formation of nanostructured surface layer. Okay, this is surface layer becomes a nanostructured layer. So this is the advantage. The surface mechanical alteration treatment, you could be able to modify. Actually, nanostructured materials have found a lot of applications. In general, nanostructured materials they have excellent hardness, excellent wear resistance, all those things are there. There are many improvement in properties, but it is not necessarily like treat methods like EQ channel angular pressing, all those methods. They are known for bulk deformation. Entire material is deformed. But there's no need to deform the entire material. You can deform and impart the nanostructure only in the surface layer is good enough. That is the idea of this method, surface mechanical alteration. So when we impinge the substrate material, the stainless steel material with the 5 mm dia steel balls for about 2,700 seconds, automatically you develop a nanostructure layer on the surface. And there will be mechanical twins induced in the microstructures. There will be formation of rhombic blocks and twin interactions, the formation of alpha prime martensite. So you can able to see these things. When you increase the ball size and treatment time, automatically, the extent of deformation is very high. You could be able to see the formation of rhombic blocks completely here. Okay, this is the nanostructure surface layer, the top surface. And you could be able to see a lot of rhombic block formation and mechanical twin formation. So we can be able to understand, you can use scanning electron microscopy to effectively understand how the microstructures are changing during a process treatment. The same surface mechanical microstructure treatment, and you can understand, you can analyze the extent of plastic deformation and how much phase transformation is taking place by using electron backscatter diffraction pattern. So this is a very good analytical technique, say attached with the scanning electron microscope. Okay, so what we did is basically we analyze the structure. Okay, so this is from the surface to the bulk. Okay, and the top layer, you could be able to see the top layer. The grain sizes are very much refined. Okay, so what happens is it confirms that nanocrystallization of the surface has occurred at the only at the top layer, and you can able to measure up to what micron it has. So with increase in size, there is an increase in the grain size from the surface to the bulk. So that confirms we are able to by doing a smart treatment, it is possible for us to prepare a graded layer structure by the application of spectrum. So this can normally we cannot able to see by other methods. If you take if you prepare a proper sample and do electron backscatter diffraction pattern, you could be able to see the formation of nanostructure surface layer as well as the formation of a graded layer structure, which would be very difficult to determine by other methods. You can see by SEM to some extent, but electron backscatter diffraction pattern clearly shows the grain size. You could be able to see it's on a final grain size. There will be intermediate grain size, and when you go to the bulk, towards the bulk, that automatically the grain size is very high. So you could be able to see that very well, and you could be able to see, analyze I said the phase transformation. So then during this impingement, what will happen is generally stainless steel is austenite phase. Okay, austenite phase will be very high generally. But when you do an impingement using steel ball, there will be a phase transformation from the austenite phase to the martensite phase. So using electron backscatter diffraction pattern, we can able to quantitatively determine how much is transferred, how much phase that's transferred. So this is the area where the transformation is maximum during the nanocrystallized area, and with increase in depth from the surface to the bulk, the extent of martensite formation is decreased continuously. So we can totally calculate up to what depth of martensite formation is there, and we can able to calculate how much volume fraction, total fraction. See, initially before treatment, it will be totally 1. It will be completely austenite phase. But after treatment, about 24% of martensite is formed after 25. So depending, you can vary the condition. This is for 8 mm diaball for 60 minutes. So you can vary the condition. You can able to determine how much phase transformation for different process variables, different treatment treatment time, different ball size, and the materials, all those things. So it is possible to use the analytical method like electron backscatter diffraction pattern to understand the mechanism of deformation, plastic deformation, and the mechanism and how much the phase transformation from one phase to the other phase, all those things we can able to understand. Right? So this again, electron backscatter diffraction pattern. These are the inverse pole figure maps as well as the phase contrast maps. So inverse pole figure maps clearly shows from the different depths it has taken. Okay, the top layer is nanocrystallized surface layer, but with the increase in depth, you could be able to see the size of the grain size is very high. Okay, this the top surface is very low, and then with the different depths we have taken. And again, the martensite formation, the top layer, the martensite formation is very high, and if we go in depth, martensite formation is very less. So you could be able to use electron backscatter diffraction pattern very effectively to understand the mechanism of deformation and how much the extent of phase transformation also. So it's a very good analytical method for materials research. We have also done the fretting corrosion of titanium alloy. Okay, titanium alloy, they are normally used to develop implant materials, because I said titanium is highly corrosion resistant. Generally, implant materials are made of titanium alloy. Okay, and the fretting corrosion phenomenon, I already said it's a small amplitude vibration, small amplitude movement. So where the fretting corrosion in a titanium implant comes means it is mainly in hip and knee implants, hip, knee, and shoulder implants. So where now the human walking frequency is about only 1 Hz. With the small amplitude vibration, automatically the fretting corrosion will come. So if you look at that implant, the hip implant, automatically it's a bone and socket assembly, just press fit. So there will be movement. And with the time, there will be fretting, movement of a fretting, mechanical damage, and there will be corrosion also. Automatically, the pieces will come down. There will be loosening of the implant. So that is a major failure. So we have studied the fretting corrosion behavior of titanium alloy with the different modifications and other things. Okay, and how we can use the surface profilometer method, surface profilometry, to understand the mechanism of fretting corrosion. Okay. We have studied the fretting corrosion of titanium 6 aluminum palladium alloy in artificial saliva. Saliva. In artificial, you can create an artificial simulated solution of saliva, and we added varying concentration of fluoride ions. The purpose is why we are bringing in fluoride ions is this is to study the fretting corrosion of a dental implant. Okay, suppose we are putting a dental implant, titanium implant, And normally in the paste that we are using, it contains a lot of fluoride ions. So it is estimated that they go up to 1440 ppm of fluoride, maximum concentration of fluoride in a toothpaste. And during this brushing, you are likely to create some vibrations on the implant, small amplitude vibrations on the implant. And so what happens in the artificial saliva and containing fluoride ions, how much it is degraded? That's what we analyzed. So it's a small amplitude vibration. The total length is about 180 microns again. So this is the damaged zone. We have taken it SEM. We could not be able to understand much from the SEM. We could be able to see there is some damage, but we could not be able to understand the mechanism of degradation. We have varied the concentration of fluoride from 0 ppm, now 190 ppm, 570 ppm, and 1440. There is not much change in the damage is clear, but we could not be able to predict much about the mechanism and how the failure is forming and other things. So in this case, we are used the surface profilometer. The advantage of using the three-dimensional surface profilometer, this is a non-contact three-dimensional surface profilometer. You can observe the image and you can be able to measure the depth, the z-axis also. In a conventional two-dimensional image, you could be able to measure the x and y axis only. But in a surface profile measurement, three-dimensional surface profile measurement, you could be able to measure the z-axis also. So we could be able to calculate the entire wear volume. It is worn out during friction, during the fretting corrosion. It is completely worn out, and you have created a whole type of structure. Okay, this is the damaged area. Okay, this is the damaged area, and we can able to calculate the wear volume by using the x and y and z-axis values. So when we calculated the wear volume, what happens is when you have in the absence of fluoride, the wear volume is about 3.26 into 10 power 12 millimeter nanometer cube. And when we added fluoride ions, about 200 ppm of fluoride ions, it increased from 3.26 to 9.87. So the wear volume is increased. So the fluoride ions started attacking the material. Generally, magnesium is good in fluoride medium. Titanium is very bad in fluoride medium. The moment you bring in titanium to fluoride contact, it will immediately attack. Okay. So the fluoride is then started attacking and then developing a bigger hole in that. Okay. So, but what happens is when you increase the concentration of fluoride to 570 ppm, there is a decrease in the wear volume. When we increase to 1440, there is a considerable decrease from 6.92 into 10 power 12 to 3.60 into 10 power 11. Look at the size, this is considerably decreased. What is the reason for that? Because generally we consider that fluoride ions are very aggressive. And with respect to titanium, fluoride ion undergoes a lot of corrosion, rapid corrosion in fluoride medium. So how come when you increase the fluoride ion concentration to 1440, there is a decrease in the wear volume? What is the mechanism? So we try to understand that. So what happens is when the concentration of fluoride ions is very high, definitely the attack is there. And the metal is removed. But what happens is, this is again that we are vibrating against the aluminum ball. Okay, we use the aluminum ball as a counter body. And the aluminum ball only is fretted around the surface of the titanium. So fluoride will attack the titanium. But what happens is, during that fretting the corrosion, there will be a lot of debris generated and they stick onto the aluminum ball. They stick onto the aluminum ball. So the configuration, the contact configuration is changed from aluminum ball and titanium to, okay, it is a titanium coated aluminum ball against titanium. So that's what happened. So when the counter body is coated with the titanium, automatically the titanium is rubbing against titanium. There won't be much removal of the material. So that is why the wear volume is coming. So since it is, but it is very difficult to predict such thing based on only the SEM. So we have to use multiple analytical techniques to understand the behavior, the fretting corrosion behavior, because normally is not visible by human eye. You cannot see, even though it's a damaged area. The damaged area is restricted to more than 200 to 300 microns. You cannot able to visually see by naked eye this damage. We have to necessarily use a scanning electron. But even if you use a scanning electron microscopy, we cannot able to understand the mechanism. We cannot able to predict which is better, which concentration is crucial. That we cannot able. But using a surface profilometer, we could be able to clearly understand the mechanism of it. And I'm going to talk about thermogravimetric analysis. So we recently prepared a composite material. Say, for example, we prepared a hydroxyapatite and graphite carbonate. You know about hydroxyapatite and graphite carbonate. Graphite carbonate is a well-known visible light photocatalyst, and hydroxyapatite is a very good biomaterial. And we prepared a composite of hydroxyapatite and GCN. And after preparing the composite, we want to analyze how much HAB is there and how much GCN is there, because it's a single powder. Okay. So for that, we have used thermogravimetric analysis. So how analytical technique can be effectively used? We have done TGA and we recorded up to 700 degrees centigrade at a heating rate of 30 degrees. No, okay. So what happens is the residual mass is about 69% up to 700 degrees. We know that hydroxyapatite is highly stable, thermally stable, up to more than 90,000 degrees centigrade. But the graphite carbonate started to decompose at about 600 degrees centigrade. And when we reaching 700, it completely decomposes. So we ran that TGA curve to 700 degrees centigrade. And initially there is a small loss above 2.5% due to removal of moisture or water. Okay, absorbed water and all. And subsequently, there is a loss. The residual, based on the residual mass, using the loss of water, we calculated the amount of HAP as 69.59%, approximately 67%. So if the HAP is 67%, we can indirectly calculate that the amount of GCN is 33%. So in the composite mixture that we prepared about HAP GCN is 67% HAP and 33% GCN. So using a thermal analytical methods, we can effectively use this methodology can be used to calculate the percentage, a fraction of different individual components in a composite mix. So we also worked on corrosion and scaling and all, and we have developed a simple electrochemical method, an accelerated electrochemical method to screen scaling inhibitors. Scaling is a major problem, okay, in cooling water systems. In cooling water system, they use for heat exchangers to control the temperature of heat exchangers. They use water, so they separate water to cool down the systems. Okay, but water is no. Normally they don't use distilled water and all in lab purpose. They use in Ennur thermal power plants in Chennai. In Ennur thermal power plant, they use even brackish water. So there will be a lot of susceptibility for microorganisms and scaling problem. Normally, even in normal tap water, there will be calcium very high and magnesium is very high. So they'll lead to scaling. Okay. So the susceptibility of the water for scale formation depends upon the level of calcium hardness and the bicarbonate alkalinity. These two factors are very important. How much calcium and bicarbonates are there. So, but once a scale is formed, that lead to other problems like that could be able to create a crevice corrosion problem, and that will affect the efficiency of the heat exchanger, the deterioration of the heat exchanger. All these problems are there. If you look at the scale formation, then the most commonly found material, chemical material, is calcium carbonate. Okay, so many people are selling, inhibitors that their compounds are very effective. And particularly the phosphonates-based compounds, they are very effective in preventing the scale formation. So normally in the thermal power plants and all, people are using, wherever cooling water systems are used, they are buying these inhibitors. So what is the guarantee that the inhibitor will work, or what is the efficiency of the inhibitor, whether it will work properly or not? So how to evaluate? That has to be done quickly. We cannot wait for hours to the. So we have developed a simple electrochemical method. So what we did is we have taken calcium chloride and sodium bicarbonate, because these factors are very important, calcium and bicarbonate. So we've taken 0.1 molar calcium chloride and mixed it with 0.05 molar sodium bicarbonate in order to avoid initial rapid precipitation. Because if you mix calcium chloride and sodium bicarbonate, immediately it will form a precipitate of calcium carbonate. So to avoid that, we have added 0.02 molar EDTA also as a compressing agent. So that can complex the calcium, and then it won't freely makes the calcium ions freely available for precipitation or formation of calcium carbonate. So there is no formation. Since we have added the complexing agent, there is no precipitation in the solution. The solution remains clear. But it can this solution can be used to deposit calcium carbonate on the cathode. So basically, we want to develop an electrochemical method. What we did is we have taken two electrodes. One is made as a cathode and connected to the cathode terminal of that rectifier. Another is connected to the anode terminal of the rectifier, and we applied potential. Okay, about 3 volts or something like that for about 1 hour. What happens is automatically the calcium carbonate forms a precipitate on the cathode. Okay, there will be ionization and there will be formation of there will be rise in pH at the interface at the cathode solution interface, and that promotes the formation of calcium carbonate deposit on the cathode material. In the same solution, you can add the inhibitors, scaling inhibitors. People are selling scaling inhibitors, or you might have developed a scaling inhibitor which could be able to inhibit the scale formation. So if you add that scale inhibitor into the solution, and you can able to measure the amount of calcium carbonate deposit formed on the metal on the cathode, you can weigh. When initially you can weigh the sample or the cathode sample, and after depositing for a particular period of time, say for example 3 volts for 60 minutes, you can wash it and dry it and take it away. So you know how much calcium carbonate is deposited. Okay, in the same solution, if you're adding different concentrations of a scaling inhibitor, you can able to find out how much calcium carbonate is forming. Okay, based on that, you can fix the optimum concentration of a particular inhibitor that you are developing, or whether the inhibitor is efficient or not. How much percentage you could be able to offer to prevent the scale formation. So these methods you can use it as a simple analytical method only, simple electrochemical method. Cyclic photometry is a very good analytical method, electrochemical chemistry. And that can be used to measure the porosity of a coating, particularly phosphate conversion coating. These phosphate conversion coatings, they are very much used as a paint pre-treatment. This is a paint pre-treatment, and it is widely used in automotive industries. Normally, your car chassis and scooter chassis, everything, it is coated with phosphate. You might have seen, the Godrej bureaus and the furnitures. They are of very good quality. So why? Because their company, they are after making the steel bureau or the table, they are doing a phosphating operation. So initially they apply a zinc phosphate coating. Over that they are applying the paint. So the prime advantage of the phosphate conversion coating is the phosphate conversion coating is insulating in nature. So when you transport furniture, okay, there may be some damages during the transport. So what happens is there will be when it is exposed to the atmosphere, there will be corrosion on the damaged area. Okay, so if you don't apply a phosphate coating, what will happen is the corrosion will spread underneath the paint, and the entire paint film will fill off. There will be delamination of the paint coating, so it becomes very ugly. Okay, so if you apply a phosphate conversion coating on the steel, and then you apply a paint film, okay, what will happen is even if there is a damage during transportation or something like that, the corrosion will be there. Corrosion will there will be corrosion on the damaged zone, but it will be localized only to the damaged zone. It will not spread. So the idea of phosphate conversion coating, it prevents the spreading of underfilling corrosion. Okay, so that is the idea of applying phosphate conversion coating for automotive materials and other things, even for your household appliances like washing machines and everything. It is applied by phosphate coating before the painting application. But the phosphate coating is porous. Any coating for that matter is porous. There is no such coating as a completely pore-free coating. There will be some amount of porosity will be. Porosity is like a hole, that uncovered area. So through that, moisture or electrolyte can penetrate through that and start corrosion on the base. So how to estimate the porosity of a conversion coating, phosphate conversion? How cyclic photometry can be used for that? Okay. So the method base is based on the oxygen reduction current density. So you can take an electrolyte like 0.1 normal sodium hydroxide solution. Okay, and there will be cathodic reduction. There will be dissolved oxygen will be there in the solution. So when you apply, when you run a cyclic photometer, what happens is oxygen will reduce. Okay, and that will lead to generate a current density, particular current. So the cathodic reduction of oxygen occurs at uncoated areas. So when you run a cyclic photometer of a zinc phosphate coated steel in 5% sodium chloride solution or something like that. Okay. The anodic peak observed between 550 millivolts and 950 millivolts, okay, is due to the oxidation of iron, leading to the formation of ferrous ions or complex compound in the pores. Because uncovered areas only the corrosion attack will first be there, because the other areas are covered by the coating. Okay, so there will be an anodic peak around minus 800 millivolts. Okay, that can be referred as the porosity peak. So this is the peak. You can able to see around 800 millivolts. You can able to form a peak, anodic peak, and that is mainly due to the dissolution of iron, oxidation of iron, leading to the formation of ferrous ion, or it might form some complex compound in the pore itself. Okay, so we can able to use the peak height or the area under the peak. So that can be give you a measure of the porosity of the phosphate coating. So even electroanalytical technique methods like cyclic photometry can be effectively used in materials research to understand, to estimate the porosity, because the porosity determines the extent of corrosion resistance offered by the phosphate coated steel. So these are some of the examples that And the same method, the porosity of the phosphated steel, can we do it by ferroxyl method? That is also a good simple analytical method. No, normally, you know about the ferric reaction. Okay, that leads to the formation of a Prussian blue color formation. So the same reaction is exposed. So when there is a porosity in a phosphated steel compound, you can take a potassium ferricyanide solution. Okay, you take a potassium ferricyanide solution and you can immerse the filter paper. You take a filter paper, immerse the filter paper in the potassium ferricyanide solution and apply it over the phosphated steel. What will happen is the uncoated area, the bare steel will be exposed. Okay, there will be small amount of acid. The solution will be slightly acidified. So that slight acid will start to attack on the base metal. So in the moment, immediately ferrous ion will come into this. Start to come, and the ferrous and ferric will react. Since the potassium ferricyanide, the ferrous and ferric will form a Prussian blue color formation. So where are the uncoated areas? You can able to count the number of blue spots, and you can tell when the porosity is there. You suppose if some of the area is not coated properly, it will be appearing as a blue patch. So you can able to see that the coating uniformity is there. The how much porosity is there. The small pores or bigger pores are there. The uniform size of pores. The very simple method you can do that. The same thing you can do by deposition of copper. This is galvanic plating. Okay, so suppose if we take a steel and then immerse it in a copper sulfate solution, since the potential electromotive, as per the electromotive series, the potentials are totally different. Immediately copper will get plated on steel. Okay, so the same method, same thing. Copper will be again plated on aluminium. So we have developed the method called how to estimate the porosity of a phosphate coated aluminium. So phosphate coating can also be applied on non-ferrous metals also, like aluminium and magnesium. So if you apply it on aluminium, okay, what happens is you can immerse it in a copper sulfate solution. Okay, so that's what we did. What we did is we take prepare the coating by electrochemical method. We apply the different current density and coat the sample. And this is the uncoated aluminum sample. So if we immerse it in a copper sulfate EDTA solution for 2 hours, and the amount of copper that is plated, you can able to determine by weight gain, or you can strip it and analyze by the AS also. So the amount of copper deposited on untreated aluminum is very high. It's about 1.82, like that. But if you coat the aluminum with phosphate coating, you can see that there is a considerable amount of reduction in the copper deposit, because most of the areas are covered by the phosphate coating. Only a few spots are left, and that areas only are copper is plated. When we go for a very high current density coating, okay, 5 milliampere, the surface is completely covered by the phosphate coating. And the amount of phosphorus, the amount of copper deposition is only 0.03. Okay, so in milligram per centimeter square. So you can able to use this method, very simple analytical method, chemical method. You can able to estimate the porosity of a coatings. Okay. Current time transient is one of the electrochemical methods that's normally used to follow the corrosion cable. Okay, it is simply a measure of the change in current as a function of time. It's called current time transient. Okay, so how it can be used to understand the corrosion behavior of phosphate coated aluminum. So that's what we did. So what we did is, we follow the change in current as a function of time. We immerse the uncoated as well as coated sample in 3.5% sodium chloride solution, and apply a potential of minus 650 millivolts. So we apply a potential of 650 millivolts for the standard column electrode and saturated column electrode, and then we measure the change in current as a function of time. For untreated aluminum, you can able to see there is a continuous increase in current. Okay. Suppose if we use the same experiment for coated sample coated at 2 milliampere and sample coated at 5 milliampere, the current is very, very less. So we could be able to appreciate that there is a considerable change in the current density. So this material is undergoing corrosion at a faster rate, and these two materials are not corroding much faster. Suppose if you want to distinguish among these two, what will happen? You slightly increase, you make it a slightly anodic. So you apply the potential to minus 500 millivolt. You increase towards the anodic side. Automatically, there will be increase in current also. Here it is only 6 milliampere per centimeter square. Here up to 14 milliampere per centimeter square. And the rest that you could be able to distinguish among the material coated as a function of current density. Okay, even here it is 4 and 5. It is not that much distinguishable. It's about the same. Okay, again you increase the anodic current. Okay, say for example, make it by minus 300. Then you could be able to see. You could be able to distinguish using the current temperature. So current temperature can be very effectively used to measure the change in current as a function of time that can be correlated to the rate of corrosion. So many methods can be, analytical methods can be effectively used for monitoring the, for understanding the materials research. So this is the end of my first presentation. So if you have any questions, you can ask. I'll be happy to answer.
Respected Professor.
Yeah.
It's a compilation of great work. Just a few basic doubts, Professor. In the dithiazone method,
Yes.
You are using chloroform acetic acid.
Yeah.
In the case of chloroform, we can use carbon tetrachloride. Is it possible, Professor? CCl4?
But if CCl4 is also undergoes, normally they recommend chloroform as a solvent for dithiazone. We have to check the solubility of dithiazone in CCl4 also, because the dye should be, the material should be completely dissolved. So first we should check the solubility, and then we have to check the photochemical stability of the solution. Because if the chloroform or dichloromethane undergoes photochemical degradation, then there will be generate a phosgene, and that could be able to abstract the hydrogen from the dithiazone. That leads to the destabilization of the reagent. So we are mainly looking at the reagent stability. So if you have to use a proper solvent, then only we can have the reagent solubility. The normal recommended solvent is for this one is chloroform. So that's what we did, and we have added acetic acid in the medium so that we can increase the stability of the solution from 1 day to 1 month. And we have tested the stability of the solution by exposing the solution to sunlight, and we are putting it in the fridge also. So we could be able to see it is stable for more than 1 month. There won't be any change in the absorbance for 1 month. Because if there is a degradation in the reagent, okay, then we cannot, that absorbance will be continuously changing. So absorption of the reagent should be proper. Then otherwise we cannot able to use it for a determination of heavy metals, for how much concentration of heavy metals is there. It is very difficult to analyze the lead.
Yes, thank you, Professor. And the second doubt, Professor, the basic doubt. Actually, in the magnesium, measurement of absorbance compare with rate of corrosion.
Yes.
In that magnesium metal, lithium is a diagonal relationship with the magnesium. So we can is it possible to make a small patch, a small chip of lithium on the magnesium, so that we can use it as a, in the place of pure magnesium, we can use it as a small patch of lithium on the magnesium.
But lithium will also undergo corrosion. No, lithium will also undergo corrosion when you put it in the medium.
Oh, yes, yes. Lithium also. I thought it will sacrifice. Okay, lithium also undergo corrosion. Yes, Professor. And the thing is, another thing, Professor, potassium ferricyanide.
Yes.
So,
yeah.
We can use the mixed ligand type of iron complex. Cyano-ammonia mixed ligand type.
Well, actually, with that, we used that. This is a standard method. It is not developed by us. It is developed by many other scientists. Actually, they have used the potassium ferricyanide solution to identify the uncoated areas. So we are taking a steel material and we are coating with the phosphate. Okay. So there may be porosity, or there may be uncovered areas, or some areas might not coated properly. So how to identify the defects and the pores? So for that, I use the potassium ferricyanide solution, because the ferrous ion that is dissolved from the steel reacts with the potassium ferricyanide and forms a Prussian blue color formation. So if you take a filter paper and immerse the filter paper in the potassium ferricyanide solution and apply it over the coated steel. So wherever the spots that is not covered, or there are some defects, immediately metal will dissolve, because the solution is slightly acidic. Okay, the metal will dissolve, and it will from the metal it is dissolving means only ferrous only is coming. So ferrous immediately reacts with the ferricyanide solution and forms a Prussian blue color. So wherever the Prussian blue color spots are there, so these are the defective areas they have identified. It's only a method to identify the areas where there is a defect of the pores. Yeah. For that, if you want to coat it on aluminum, you can use some other complexing agent, definitely. Okay, if you want to coat it on magnesium, then you can use 8-hydroxyquinoline also as a complexing agent. As long as it is giving some color, it is fine. You can able to use it.
Thank you, Professor. Thank you.
Thank you, sir. It's a very nice presentation. My question is related to chloroform and acetic acid. What is the exact mechanism behind it? The acetic
That's what
acid
I said, no.
act as a anti-photosensitizer?
Yeah, actually, what happens is that when this is a photochemical degradation. See that when the reagents are dissolved in chloroform, and then when you expose it in the higher temperature or particularly visible light, what will happens is that chloroform degrades and then that generates phosgene, and that abstracts the hydrogen from the diffusome. So that leads to the reagent instability. That affects the stability of the reagent.
Okay.
So you cannot use it for a longer, but particularly when the solution is dilute, automatically the absorbance keeps varying, and that's it.
Okay. Okay, sir. Thank you, sir.
Now, in this presentation, I just want to highlight some of how analytical chemists can work on different problems on materials research and then develop new methods for a better understanding or better analysis purposes. So that's what my idea.
It's a very nice presentation, sir.
Yeah.
Thank you, sir.
Yeah.
Other participants also discuss their theories with us, sir, about the topic.
Namita ma'am, Nina is interested to ask some question. She is raising hand. Nina. Please allow her to ask. Dr. Nina.
Ma'am, Shadab sir, we have to request to the Shadab sir.
Okay.
Ma'am, then you write the question on the chat box.
Dr. Nina, please write the question in the chat box. Is Shadab present in the meeting?
Shadab sir, please allow the participants for discussion. Technical team is requested to please allow the participants for discussion. Till now, participants, please write your question in the chat box.
So till Shadab sir allows participants to discuss, can you throw some more light on corrosion inhibitors and scale?
Sorry? What is the question?
Sir, can you throw more light on corrosion inhibitors and scale inhibitors?
Yeah, corrosion and scaling inhibitors. Okay, scaling, is a major problem in cooling water cycles. Corrosion is a problem universally, because you are experiencing, when it's exposed to the atmospheric, there may be atmospheric corrosion, there may be aqueous corrosion when you are dealing with the different mediums. Okay, different acid environment or saline water, seawater environment, or all those things are there. And inhibitors basically they work by an absorption mechanism. Say many material, anything can be, most of the organic compounds can be used as corrosion inhibitor. Basically, because the organic compounds absorb on the surface of the material. As I already said, corrosion is the definition of corrosion is the interaction between the metal and the environment. Okay, it's a two-component system. Normally, it is very difficult to change the environment. So we modify the material in the form of a coating and other things that alloying or coating that we do. So for example, steel is a normal material. Steel undergoes corrosion. So we add some alloying elements like chromium and nickel, and we make it as a stainless. Okay, so stainless steel is not corrosive. It's not undergoing faster corrosion like steel. Steel usually undergoes corrosion. Okay, and if you want to apply a coating, you can apply a coating. You can apply a paint coating. You can apply a phosphate coating. You can apply a metal coating, nickel coating, chromium coating. So what we are doing is we are physically separating the metal and the environment by the reaction, so that the metal did not corrode or deteriorate. Okay, that's a mechanism for the thing. So, how you can modify the environment? Environment modification is always not possible, but some of the environment, say for example, if it's an aqueous corrosion behavior, then you can add the corrosion inhibitor into the environment. Okay, so the corrosion inhibitor is supposed to absorb on the, these are all chemical compounds only. Basically, say for example, if you're taking an acidic medium, amines will work as a very good corrosion inhibitor. So if you add amines, particularly long chain amines, they will go and absorb on with the polar group, and then the hydrophobic tail will be wagging around, and then that repels the approach of water and other things. So you can able to prevent the approach of the electrolyte towards the substrate, metal substrate, and then automatically that can able to inhibit the corrosion of the material. So these are the things. Scaling, it is mainly due to the formation of calcium carbonate. So that case, your inhibitor should be able to prevent the formation of calcium carbonate. So mainly phosphonates-based compounds are used as a scaling inhibitor, because that it could be able to form some complex with the calcium, and then it won't allow enough release of enough calcium, formation of calcium carbonate. So that is the mechanism of the scaling inhibitors. Corrosion inhibitors may be of a different type. Okay, they may be mostly organic compounds. Whether you use it for acid environment, use it for aqueous, so seawater environment. So depending on that, we can choose what are the type of material, chemical compounds.
Thank you, sir. Thank you very much. Sir, one more query I have.
Yeah.
That if any researcher want to develop a method, new method, so what they should keep in mind while selecting solvents? So can you throw some light over it? So what precaution we should take while selecting solvents for the method of any compound of interest?
So the same example, no, this one itself we can take, because the recommended solvent is chloroform, and already Dr. Kumar has discussed about the changing solvent, whereby instead of chloroform, you can use CCl4 or some other method. So, but we have to see the solubility and the other factors, and we have to see how the dielectric constant of the solvent is going to influence the absorbance phenomena, whether there is any change in the molar extension coefficient, all those things that we have to see. And even if you are adding a 6 molar acetic acid, there will be viscosity will be increased, and then that should not have any other influence on other properties. So that and all we have to keep it in mind. That, since it is a spectrophotometric method, there is not much problem. But if it is by some other method, then we have to see whether no addition of acetic acid is going to increase the viscosity of the solution. So whether that will have an effect or not. So that aspect we have to see.
Sir, may I ask one question, please?
Yeah, sure.
Sir, can you please guide us from where we can perform the SMAT of our samples, nanoparticles? Sir, if I want to perform the SMAT for my prepared samples, which are nanoparticles.
I could be able to see.
Sir, is there any?
What method?
Sir, is there any lab, particular lab or research center for SMAT?
Surface mechanical iteration treatment.
Yes.
The surface mechanical iteration treatment is not like ball milling. It's similar to ball milling, but that involves metal samples, not powder samples.
Yes, sir.
So for preparing nanomaterials in the powder form, you have to use ball milling. Ball milling is also a similar phenomenon where you are putting the powder, and then you are putting the grinding media like alumina or zirconium balls, you can use it, and then you mill it for several hours. Okay, then automatically when the particle gets trapped between the two different balls or between the walls of the container and the ball, so automatically there will be a reduction in the size, so you could be able to prepare nano size material. So basically what you need is the ball mill. Ball mill, many people will be having it. Ball mill, many people will be having it. You can contact people. You check overall working on ball milling. Prepare synthesis of nanomaterials by ball milling. You can put it in the literature, and then automatically papers will come. You can contact the authors, so they can help you.
Okay.
You can supply the material.
Okay,
do the powder, and they will do it.
One question is in the chat box.
Yeah.
This is from Ma'am Karuna. why you use Boltzmann fit curve for plotting the graph between absorbance with respect to pH variation.
Yes. No, actually, we measured the absorbance as a function of time. We measure the pH as a function of time. So we want to see, is there any, both are time, the x-axis are both are timeline scale. So we want to see the correlation between the change in pH as a function of time, as well as the change in absorbance as a function of time. So when we plot absorbance versus pH, then we could be able to see a very good correlation between the pH, change in pH measured at a particular wavelength and the change in pH. So we said that we could be able to see, since there is a very good correlation between two parameters, we thought that instead of measuring the pH of the change in pH of the medium, we can measure the change in absorbance of the solution as a function of time. That may be a very good method to follow to monitor the corrosion behavior. That's what.
Thank you, sir.
There's a question, why you use Boltzmann curve for plotting the curve? No, Boltzmann curve they asked actually.
Yes,
actually,
yes.
we have to follow, no, we tried a different fitting pattern and then it is not linear throughout. It is, initially it is a linear to some extent. After that it is getting saturated because I already said during the corrosion of magnesium corrosion product will form. Okay. Yes, sir. So it is not linear throughout. So it initially magnesium undergoes corrosion and then it forms a corrosion product of magnesium hydroxide on the surface. So once the corrosion product is formed, the extent of change in pH as well as the extent of change in color is a function of pH. So there won't be much dissolution, there won't be much change in pH. So it's getting saturated. So that is why we use the Boltzmann fit curve, okay, to see that how the changes in fitting the curve, how the changes is there. It is not linear throughout. We cannot apply a linear equation for that. Thank you.
Thank you, sir.
No more questions?
And if you have time, I can make one more presentation about my research program and vacation. Or if you want to close it, you can close it. That depends on the time.
No, sir, if you would like to continue, we would be...
Maybe I will give you 15 minutes brief about my research.
Yeah, sure, sir.
That will be fine.
Most welcome. Please share.
I already said that we are working on magnesium-based implants. Okay. So some of the things, and so generally we believe that implant should be highly resistant. Okay, there are a lot of implants: dental implants, shoulder implants, hip implants, all other things. Now these are the stent materials. I was mentioning about the small stent materials, and these are the hip implants, and these are the shoulder implants and knee implants, etc. Different types of implants. So generally, the common belief is that implants must be highly corrosion resistant. It is not actually necessary. So if you look at the evolution of biomaterials, when the first generation of biomaterial is the material should be highly inert, and then they say that then comes the next generation. They say that it should be bioactive. It should ensure a more stable performance over a longer time. Okay, and we have come a long way, and we have faced many challenges. And we are entering the third generation, which is talking about biodegradable implants. So what are biodegradable implants? They are implants that can chemically degrade or decompose within the body itself. So once implanted, what is a biodegradable implant is? Once implanted, they should maintain their mechanical integrity until they are no longer required. Okay, and they should be absorbed and excreted by the body, leaving no trace in the body. So this is the basic definition of a biodegradable implants. So like Nike advertisement, they do their job and disappear. Okay, just do it. So that's the concept. So when we are talking about degradable implants, you have two different choices: polymers and metals. I already said polymers are not stable. Okay, thermally, chemically not stable. Sorry, they don't have enough mechanical strength. But metals have mechanical strength. So magnesium, iron, and zinc. Among that, magnesium is a preferred choice because magnesium is not toxic. The first thing, because we are putting a material inside the human body, it should not be toxic. That is the first criteria. So magnesium is not toxic. In fact, magnesium is required for the human body. The everyday requirement of a human body is about 200 to 300 milligrams. Okay, so in fact, many diseases are correlated to the deficiency of magnesium. Okay, so even if the magnesium is dissolved in excess, it is not going to affect the human body. Okay, so there won't be any adverse side effects. So that is the main advantage. Okay, and it is beneficial to bone growth, and the specific density and modulus of magnesium are much closer to the bone when compared to the titanium or chromium, cobalt, molybdenum, molybdenum, etc. And because of that, it decreases the stress at the implant interface and increases stability of the material, and it can stimulate the bone growth by dissolving through the media and all those things. And magnesium possesses a higher fracture toughness. Okay, it takes part in the metabolic reaction. It is also a cofactor in DNA and RNA. Many important aspects are there. But the major limitation of magnesium in using it as a biodegradable implant is the rapid corrosion, because magnesium is highly active and body fluid is highly corrosive. And during that process, when there is a dissolution of metal, the side reaction is evolution of hydrogen. So when it rapidly corrodes, there is a large volume of hydrogen gas. And if you are using it, magnesium as a stunt material, there will be accumulation of hydrogen bubbles in gas packets adjacent to the implant, and that would delay the healing of wound. It could lead to necrosis of the tissues, and if the size of the hydrogen bubbles are large, that could increase the risk of blocking. When you are putting it the heart arteries, there may be a blockage because of the hydrogen bubble evolution. So that needs to be how to control the rate of the evolution and corrosion. And there will be increase in the local pH that will affect the physiological imbalance. Those things are there. The problem is iron undergoes uniform corrosion. It removes layer by layer. But magnesium undergoes pitting corrosion. You see that pitting corrosion. So it drills deep. So it's very, very bad. We cannot change the mechanism from localized to uniform corrosion. So that is the problem. And since it undergoes pitting corrosion, it undermines the mechanical integrity of the material. So that is the major problem with magnesium. Okay, normally we have to establish as a function of time, you need to maintain mechanical integrity up to this stage. Beyond the stage, you should be able to degrade much faster. So you should be able to hold for about 15 months. Then after that, it should degrade. But what happens is it is degrading much faster, and the mechanical integrity is becoming very poor. So that's why we have the problem of developing magnesium. Same. So if you see the requirement of magnesium as a degradable implant, first criteria, you should have sufficient mechanical strength and integrity until the affected part is healed. And you should exhibit resistance to corrosion during the initial stage. Okay, but subsequently it should corrode. How it should corrode? It should corrode in a controlled and uniform fashion. So this is asking for too much. Initially, you say that it should exist, it should offer resistance to corrosion during the initial periods of implantation. But subsequently, it should corrode. How it should corrode? It should corrode in a controlled and uniform fashion. Not only that, the corrosion product that is developed should not exceed the acceptable level of the absorption level of the human body. Corrosion, see, everything should be degraded. Material, not only material, the corrosion product should also be absorbed by the human body. Should not cause any problems. Okay, so there are what to do. So we cannot do some magics. Aladdin and use the magic lamps. Then do that. Okay. So we have to work out a proper strategy. So what is the most appropriate strategy? Is to reduce the corrosion rate of magnesium. How we can do that? We can do by adding alloying elements. We can add by surface coating, or we can do mechanical pre-processing like the surface mechanical attraction treatment or ECAP, etc. Alloying is a good choice. It can increase the mechanical strength, no doubt about it. But you cannot use all the alloying elements because we are putting it as a degradable implant. So it is going to dissolve in the human body. So that alloying element should not be toxic. Magnesium is not toxic, but the alloying element should also be not toxic. In that case, you have only limited amount of alloying elements, manganese, zinc, etc. So the best choice is surface treatment or coating. So we have developed some surface modifications and coating. One of the things is plasma electric oxidation. That basically it's a high voltage anodic oxidation process. It forms a porous oxide layer. Basically, this is the architecture. This has a thin barrier layer and over which It forms a porous structure. So that is this is the scanning electron micrograph of that, and we have analyzed the X-ray element mapping. Basically, it consists of magnesium, oxygen, and silica, the silicate electrons. So this is the idea that we have developed different materials and coatings, non-scale modifications and other things. So the basic idea of magnesium that I already said, it is highly corrosive material. It is highly corrosive in the human body environment. So it is very difficult to maintain the mechanical integrity of the material. So we could be able to achieve a limited success that magnesium can be used to develop a degradable implant only for a thin needle, like a pin or a stent material. You cannot develop load-bearing implants with magnesium. So we have many people have different opinions, and still with respect to magnesium research, we have a long way to go, because people feel that theirs is the correct direction. Other people, whatever they feel is the correct direction, and it is for a user, no, it is really a long way to go to have a magnesium implant. So I'd like to thank National Research Foundation of Korea for supporting all of my research on magnesium-based materials. Thank you.
Now all the participants can discuss their queries.
You have any doubts about?
Or any doubts about the topic?
Yes. Or the earlier talk, whatever it is, you can ask. You can ask about your research programs also. Whatever the research topic that you are doing, you can freely ask. Somebody has asked about nanomaterials and then ball milling and other things. So that type of questions also you can ask. I'll be happy to answer. Chat box. We are not able to recycle plastic. Plastic can be recycled, right? Plastic can be recycled, right? I'm not sure, but why plastic cannot be recycled? We are using plastic to put roads. No, they are using the plastic waste to make roads. So it can be made usable. It can be made usable. It's not a question that why you cannot recycle plastics. Maybe because of some cost factors they might have not tried, but definitely plastic can be made recyclable. Biodegradable. Oh, okay. That mainly because of the chemical nature of the material. Okay. So if plastic, if you have polymer, basically if you have polymeric materials, no. So I'm talking about biodegradable polymers like polycaprolactone, polylactic acid. So these are all biodegradable polymers. Okay. Plastic comes under a non-biodegradable category. Okay. It is not biologically degraded. Right. You can add some solvent, I can dissolve. Okay, it can be chemically degraded, but not biologically. It is not possible to degrade. So that is the difficulty in degrading the plastic.
Shall I conclude?
Yes.
Yes, we can conclude. Just I would like to say thanks to sir for very informative session, sir, and hope same kind of cooperation in near future too for organizing such kind of activities at our campus offline.
Yes, sure.
Thank you. Thank you very much.
I would like to come. Thank you.
Thank you.
Namaskar. There is one question.
Yeah, please.
You all focus nanotechnology based polymers. No, nanotechnology is there everywhere. No, people are because nanomaterials have unique properties. Nanomaterials have unique properties. So quite naturally, people will be working on nanomaterials area. And Polymers are no exceptions. People will be going for nanotechnology-based polymers, nanomaterials-based ceramics, and even nanostructured metals. So the surface mechanical alteration treatment that we have done is to create a nanostructured material on the top surface. So that's the thing. Nanotechnology-based biomaterial can be biodegradable. I'm not sure about it, because just because by reducing the grain size or the size of the material, is it possible to make it biodegradable? That I'm not sure about it, but maybe I will get back to you. I will see some literature and then I'll set the process.
That's very interesting topic, especially that the second short presentation that you given about the implant, because there are so many implants nowadays in every human body. So we are very curious about the material use and how it affects in our body. So it was quite interesting.
Yeah, magnesium is essential for human body. Now there is a book on in the internet you can download magnesium. Magnesium. Actually, I forgot about that. It was written by a group of doctors, and they correlated. I think magnesium water. I have coined it the title as magnesium water material, but it is something related with that magnesium related thing. It was written by a group of doctors, and they correlated all the disease, even fatigue, heart attack, stroke, problems during pregnancy. Everything is due to deficiency of magnesium, because they say magnesium controls the central nervous system, and people who are having learning difficulties, okay, they lack magnesium deficiency. Because of that, the learning difficulty is coming. The mentally challenged people, that is mainly because of the deficiency of magnesium. And they say magnesium is very essential, and magnesium is very rich in, particularly in almonds, greens, milk, and all type of seeds. Normally we are throwing off many seeds, but actually only in the seeds magnesium content is very high. So we can see, you can surf in Google, what are the magnesium rich materials, fluids and seeds and that. So that you can take a lot, because that will make you more active, because it controls the central nervous system. It makes you very much agile and active. That is very important. We have to take a necessary amount of magnesium every day. Normally, the human everyday requirement of magnesium is about 300 milligram, 300 to 400 milligram, they say. So if there is a deficiency of magnesium, then that may lead to problems. Because generally we say that the heart attack, we say people like, generally they are obese, and there will be a blockage in the heart because of the accumulation of cholesterol inside the arteries. But we might wonder that people who are very thin, very lean in their body, they also get heart attack. So in that case, where comes the cholesterol? They don't take any fatty foods. Okay, then how they are getting heart attack? So what is the reason they say that? Because of the deficiency of magnesium, the nerves are becoming like a old aged rubber tube. Aged rubber tube, it automatically stick. If you push it automatically stick together. So that is the phenomenon that is happening. It is because of the deficiency of magnesium and the aged tubes and the hot water arteries and all becoming clogged. It stick together, and then that they block the flow of blood flow, and that is heart attack. Even for the people who don't have, who don't take enough fatty foods. So that problem is coming. So magnesium deficiency is, we have to be dealing with very careful, and then we have to consult with the doctor, and then take appropriate supplements. There are a lot of magnesium supplements in the form of general foods as well as in the form of medicines, tablets and liquids are there, magnesium supplements.
Thank you, sir. Thank you for giving deep insight about the topic, especially detailed mechanism of various metals corrosion, their prevention, and the way you started how to convert the waste material into useful products. That is also interesting and main challenge nowadays for analytical chemistry. And it is interesting area of research also. Yeah. And second one was very interesting, that body implants. So I'm sure that all the
ma'am,
yes, question. Yes, Asmita.
Sir, it's a very nice topic. Your second presentation is very nice.
Yeah.
Nowadays, it is used in the implant in any form.
Which
magnesium metal is used in the implant.
Yes, it is used. It is commercialized. It is commercially available. Implants are available. They are using magnesium as a stent material. They are using magnesium in the form of a small pin. There is a minor fracture, a hairline fracture. Okay. So they put a magnesium pin to attach. So there won't be any problem. Magnesium pins they are using, magnesium small bolt type of things they are using, and the hot wall stents they are using. It is there. It is already there. It's commercially available.
Okay, okay. So main problem is the decomposition, highly reactivity of the magnesium. It is the main problem.
Yes, that is the main problem. It rapidly corrodes. It rapidly corrodes, and because the human body environment is highly corrosive, it contains a lot of chloride ions. And the moment you put magnesium in a sodium chloride environment, no, it corrodes like anything.
Okay. Sir, if the controlled corrosion is possible, then it's
that you can do.
The magnesium deficiency problems, no?
Yeah, definitely. You can control the magnesium corrosion by alloying. You can do, but I already said that no, alloying elements should also not be toxic. So magnesium is not toxic. So that we have to appropriately choose and control.
Okay. Thank you, sir. Thank you very much. It's a very nice presentation.
Thank you, sir, for a very nice session. I'm sure that all the participants definitely get benefited and learn more new things today. Thank you, sir.
Thank you. Thank you.
Really nice.